Hi, hola, bonjour, and Salaam. Welcome to Blueprint Bazaar. In part 15 of our plastic shredder machine full assembly walkthrough, we take another major step toward completing the mechanical build by assembling the gears onto the shaft and installing the bearing covers on the mounting plates. This part signifies the transition from passive components like blades and frames to active mechanical elements that enable motion transmission and machine functionality. We start by inserting the gear components that will serve as the primary elements of power transmission. These gears are meant to be coupled either to a motor or to each other, depending on the drive system you're implementing. For now, our goal is to position them accurately on both shafts and align them in a way that prepares the assembly for motion simulation and later animation. The first step in the gear assembly process involves bringing in the gear part files and placing them at the ends of both shafts. Once inserted, we begin the mating process. A concentric mate is applied between the inner hole of the gear and the circular shaft body, which ensures rotational alignment. Next, a coincident or distance mate is used to control the axial position of the gear on the shaft. This step is crucial because gear spacing must be consistent with the intended meshing mechanism, whether the gears are meant to touch directly or be offset for belt or chain-driven systems. With both gears positioned, we take a moment to perform a basic motion check. This involves rotating one shaft manually inside the assembly to visualize whether the gear teeth align as expected and if there is any potential interference with adjacent components like the frame or the bearing mounts. Even though we haven't added the motor or belts yet, getting this foundational placement correct now will make future motion integration seamless. The next section of the video shifts focus to the structural aspect, the bearing covers. These components are essential for two reasons. First, they physically restrain the shaft ends, keeping them stable under torque and preventing axial movement during operation. Second, they house the bearings that reduce friction and allow smooth shaft rotation. To install the bearing covers, we first identify the mounting holes on the frame that were designed for this very purpose. The bearing covers are inserted and aligned with concentric mates to the circular shaft ends, followed by coincident mates or distance mates to place them flush against the mounting surface. Care is taken to ensure that the bearing cover is not interfering with the shaft rotation, so the internal bore of the cover must be slightly oversized compared to the shaft diameter to allow free movement. One thing we highlight in this part is the importance of tolerance and spacing when dealing with rotating components. If the bearing cover is misaligned or placed too tightly against the shaft, it can lead to friction, heating, or premature wear during real-world use. Likewise, a loose fit could result in vibration, misalignment, or noise. So, this segment offers not only the visual technique for placement, but also the design reasoning behind every mate. After placing both bearing covers and double-checking their orientation and position, we do another brief motion check. This is done by manually rotating the shaft again and observing how it interacts with both the gear and the cover. The motion should be smooth, and there should be no collision with either the side plates or the mounting frame. By the end of this part, the assembly now has a complete mechanical loop, from blades to shafts to gears, and finally to support via bearing covers. The machine's rotational axis is now defined, and we are one step closer to simulating its functionality. This part is particularly helpful for anyone trying to understand the relationship between static mounting elements and dynamic rotational components. It bridges two crucial elements: design intent and real-world mechanical behavior. if the gears and covers are not placed with proper mating constraints and spacing. The entire machine's efficiency and durability could be compromised. Before we move toward bearing assembly in the upcoming part, it's also worth discussing how gear alignment impacts not just motion transfer, but also load distribution across the shafts. Misaligned gears can lead to uneven wear and gear tooth failure over time, especially when dealing with harder materials in shredding operations. That's why this stage, though it appears simple, plays a foundational role in setting up long-term mechanical reliability. Additionally, we touch briefly on gear orientation. Depending on the type of gear, spur, helical, or bevel, the mating process might involve different angular orientations. In our case, we're using spur gears, which require parallel shaft alignment and face-to-face engagement. This makes it easier to ensure perfect symmetry and consistent rotation during the testing phase. We also take a closer look at how the bearing covers are seated into the assembly. While their main purpose is support and housing for the bearings, their design also affects how forces are distributed into the mounting plate and frame. If the cover doesn't sit flush, or if the mounting holes are not aligned, it can skew the shaft slightly and misalign the entire gear system. That's why we emphasize slow, deliberate mate placement during this section of the walkthrough. Another key takeaway is the order of operations in this stage of the assembly. We first secure the gears, then add the bearing covers, not the other way around. This allows us to lock the gear positions relative to the shaft before encasing the ends, which helps preserve mechanical alignment during test rotations. Reversing this sequence could trap the shaft in a fixed axial position before gear placement is finalized, complicating adjustments. For those planning to motorize their plastic shredder machines, this part also serves as a helpful checkpoint. You'll want to note the available space around the gears for motor brackets, couplings, or belt systems. While we won't be adding the motor in this part, having the gears placed correctly ensures there's room for power transmission hardware and simplifies your design process when that stage arrives. Another important aspect covered in this part is the axial stability introduced by properly secured bearing covers. These components not only prevent the shaft from wandering during operation, but also absorb and redistribute forces that result from gear engagement and shredding resistance. This structural support is vital for maintaining alignment over long-term use. We also touch on how this step prepares the assembly for future animation or simulation. With gears in place and bearing covers installed, we've effectively defined our machine's drivetrain geometry. That means when it comes time to simulate torque application or rotational movement, we'll have the correct constraints and clearances already embedded in our model, saving time and avoiding rework. Additionally, this part provides a great opportunity to teach beginners about design intent behind real-world assemblies. Every mate, every positioning decision, and every motion test reflects engineering judgment, balancing ease of assembly, part accessibility, and performance efficiency. By watching and replicating this process, viewers gain not only SolidWorks skills, but also mechanical insight. To further reinforce mechanical reliability, we encourage viewers to consider how thermal expansion and operational wear might affect shaft alignment over time. In real-world applications, gears and bearings must not only be assembled correctly, but also be serviceable. Designing the assembly so that these components are easily removable or adjustable can significantly reduce maintenance downtime and increase machine longevity. Lastly, we briefly discuss gear orientation and phase alignment, especially relevant if your setup involves synchronized blade motion on both shafts. Ensuring the gears are properly phased allows for even blade engagement, minimizes torque imbalances, and leads to a smoother shredding process overall. These final checks, though often overlooked, can be the difference between a functional prototype and a production-ready machine. In the next episode, Part 16, we will assemble bearings on the shaft and notice the blade interaction to analyze movement, check for mechanical interference, and validate the integrity of the cutting mechanism before finalizing the drive system. The main purpose is to grasp the ideas shown by each short step-by-step tutorial so that you can fully replicate the model and easily understand the features used. So until next time, stay sharp and keep on building with precision. Please keep supporting us as we dive deeper into mechanical design and development. Don't forget to like, share, and subscribe so you never miss a step on this engineering journey with Blueprint Bazaar.